All right. So I'm very pleased that I have the opportunity to give this talk to LSMSA students. It's been in the idea of giving this talk has been in the back burner for years, actually. I've been in LSMSA for 4 years now, and I've wanted to give this talk like for years now, and it had to take a pandemic for it to happen. Um, Anyway, the topic that I want to talk about today is not going to be, is a little bit open-ended. I'm not going to give all the details, the ins and outs. It's going to be more like a teaser, so to speak, to how do you say it? Uh, Produce a little bit of a brain itch, so that if you're more interested, that you pursue something more, a better understanding or something more in depth of the phenomena that we're going to be talking about today. A little bit about myself. I grew in a city called Barranquilla in Colombia. Um, Over there, I pursued my a degree in teaching math and physics, which I earned as a bachelor. I earned in 2002. But in 2006, I moved out of the country to pursue a master's degree in physics, which I completed in 2009. And from 2009 to 2015, I worked in my PhD degree, which I accomplished in 2015. So it's been a while. The topic that I want to share with you guys today corresponds to the topic that I chose for my thesis dissertation, namely quantum gravitational spectroscopy. That was not actually the title of the dissertation, but that's the name of the phenomenon. It's a phenomenon that is fairly recent. Um, it was observed for it was predicted for a long time. It was thought that it was not going to be experimentally feasible, but it was actually experimentally observed in 2002. And since then, the experimental observations have been improving. And part of my thesis was to produce a means to improve the experimental observations. We had a contact with the experimental group that was based on France. They shared, they were very polite to share with us their experimental data. And what we did was use that experimental data to run a sort of a simulated version of their experiment, and then provide some um, suggestions for their observations to improve, and therefore make the phenomena much easily observed. So in this talk, I'm going to give you a broad idea of what the phenomenon quantum gravitational spectroscopy is about. In order to understand what it is about, I'm going to have to talk about things like quantum mechanics and stuff like that. I'm pretty sure that you are excited to hear this about these topics, but I'm going to um, try to keep things mathematically accessible. I'm not going to go into the whole details um, of the theoretical study that I made. But of course, if you are more interested, and that's more of the objective of the talk, to spark your curiosity and to present to you several projects that I have in mind that are connected to this topic that I feel that LSMSA students could embark in. We have the resources here, and they could be developed into something like um, a distinction project or a presentation in the form of a poster somewhere, or some sort of exposition in some sort of science event. All right, so let's start. Let's see if I can share my screen.
Yeah, share your screen there.
Um, so as I said, the shorthand version of the topic of the title rather, is quantum gravitational spectroscopy. In order to understand what this is about, we need to say one thing or two about quantum mechanics. You might be have your own background knowledge of what quantum mechanics is, what it studies. Maybe you're taking Dr. Dowling's course. That will be your first approach to this topic. By the way, cueing commercials, you are very much encouraged to take my modern physics course. It's going to be offered next spring. Over there, we talk about not just quantum mechanics, but also relativity. If you meet the requirements, then by all means, don't lose the opportunity to do it. We couldn't do it this semester uh, because of the pandemic and that stuff, but hopefully next spring. All right, anyway, um, we need to say a couple of things about quantum mechanics. The most important aspect that we need to concentrate on is the so-called duality, particle-wave duality. In the world of the quantum, particles behave like waves and waves behave like particles. And that's why we see this is a photon, which is the particle that we associate with electromagnetic radiation. Is sort of having a identity crisis there. It doesn't know if it's a particle or it's a wave. There's much more. This is an extremely oversimplified statement in regards of all quantum mechanics, or what all quantum mechanics is, but it'll suffice for today's purposes. This dual behavior of both radiation, which is a wave, and particles occurs only in certain scales. Scales where in the case of particles, the particle is very low size or very low mass. And in the case of waves, the energy scales are very high. Okay, so things like something as small as a neutron will play a fundamental role in today's discussion, will exhibit wave-like behaviors. Not just neutrons, also other subatomic particles such as electrons and protons. And electromagnetic radiation such as gamma rays, ultraviolet, etc., will exhibit a particle-like behavior. And that's all we need to know, at least for the moment, in regards of quantum mechanics. 4 mathematical tools that you're going to hear me mentioning throughout this talk that that are a result of this particle wave duality, and therefore there are 4 mathematical tools that we will use in quantum mechanics, are the following. The first of them is the so-called de Broglie wavelength. The de Broglie wavelength corresponds to the wavelength of the wave that we would attach to a given particle. So if this is a neutron, which we just said has wave-like behavior, then the wavelength of the wave, this is called a matter wave, by the way, we'll have a wavelength, the value of that wavelength, the de Broglie wavelength, will be given by the ratio of the most important constant in quantum mechanics. Probably I should have made a slide only dedicated to this constant. This constant is called Planck's constant, divided by the momentum of the particle. The momentum of the particle is just the product of the mass times the velocity of the particle. This is a postulate. Mr. de Broglie, who you can see there, is postulated, and he was correct. In his thesis, by the way, he postulated the matter wave theory. Incidentally, each branch of physics is characterized by a fundamental constant. Gravitation is characterized by Newton's gravitational constant, thermodynamics, and cueing commercials. Take my thermodynamics course next fall, okay? Next fall is going to be offered. Anyway, thermodynamics has its own fundamental constant, the Boltzmann constant. The fundamental constant in quantum mechanics is the Planck constant. You're going to see it in the equations today a lot. It's represented with the letter H. All right, so one tool, you're gonna hear me mentioning the de Broglie length later. One mathematical tool is the de Broglie wavelength. Another tool, if you're taking Dr. Dowling's class, most probably you have heard of this equation, is the so-called Schrodinger's equation. So the wave-like behavior of particles can be obey rather an equation that we refer to as Schrodinger's equation. Here's where the math comes in. Um, Schrodinger's equation is a differential equation. One of the simplest versions is the one that you're seeing here. At least the one that I had to use in my thesis is the one that you see here. One very quick way to understand Schrodinger's equation is by viewing it as a statement of conservation of energy. That complicated term corresponds to the quantum version of kinetic energy. This other term corresponds to the quantum version of potential energy. That gives me a total energy. The solution to the Schrodinger equation is what we call the wave function. The wave function is a mathematical tool that describes, as the name suggests, the wave-like appearance as time goes by. What is the shape of that matter wave that is, well, and other features of that matter wave that is representing the particle. For reasons that we don't have time to go into, the wave function itself is not physically, doesn't have a physical meaning. The quantity that has a physical meaning is square. So what physicists do when they do quantum mechanics is finding the wave function and then take the square of the wave function. And that will provide information such as the position of the particle, the momentum of the particle, the energy, and other physical quantities. The third, now, before I move on to the next one, there are several ways to solve the Schrodinger equation. That mostly the solution will depend on how complicated is this term, the potential energy term. Sometimes you can solve the equation with analytically, so using some method of solution of differential equations, but all the times you have to use a computer, so, or you have to adopt some approximation. And sometimes it's not solvable at all. Sometimes you're kind of lazy, you don't want to have to go into the details, so what you do is bypass in some way the having to solve the equation, having to find the wave function. And when we introduce, oh, by the way, this was not the slide I was hoping. Let me skip this one for a moment. And what we introduce is an approximation. One very famous approximation that most probably you have heard in your chemistry class, and as much as your chemistry teacher might have insisted that it's coming from chemistry, it doesn't. It comes from physics, is the quantization rule from Niels Bohr. Niels Bohr proposed the model of the hydrogen atom in which we view the orbits of the electrons around the nucleus as being quantized, in the sense that the electron cannot orbit at any desired orbit around the nucleus of the atom, but certain orbits. You're going to hear that word a lot today as well, that the orbits are quantized. And this rule comes from the solution of this integral that you see here. But this integral is sometimes a little bit kinder than having to solve the Schrodinger equation. So one way to bypass having to solve that equation is using Bohr's quantization rule. The other tool is Heisenberg uncertainty principle, not this Heisenberg, this Heisenberg. And what this is, again, another tool that we use to do some estimates, in particular estimates of position, this is what this represents, or momentum of the particle, without having to solve the Schrodinger equation. And what's Heisenberg discovered or proposed is that for a quantum particle such as a neutron, the uncertainty in the measurement of the particle's momentum, that's this term, comes at the expense of the uncertainty in the measurement of the particle's position. That's what this term is. So if you want to determine more or less where your particle is located, then you can introduce a term for the momentum and solve for this equation and obtain an approximate value of that position. And that's one way in which You're not going to get the exact thing. That's why it's called uncertainty. You're not certain about the result, but it's going to give you like a bracket of values that that might, give you an idea of what's going on. Incidentally, the Bohr's quantization rule, the semi-classical approximation, is based on very simple observations. This was also presented by Louis de Broglie. This phenomenon that you see on the screen is called standing waves. If you are in my physics 120 class, we studied this at the beginning of the semester. So what happens is that um, when we have a string vibrating between, a 10 string vibrating between 2 points, it will vibrate at quantized, quote unquote, quantized frequencies, in the sense that it will only present a vibrational pattern at certain values of the frequency. Here we can see that that number is about 14 hertz. Every time that you double, every time that you increase the frequencies by that number, approximately, you get a new pattern. And that's how de Broglie explained the quantization of the orbits in the atom. It's just that each of the orbits correspond to a vibrational pattern of the wave that represented the electron that was sitting in that orbit. All right, so these four tools are the tools that um, you're going to hear me mentioning during the talk in regards to the mathematics of the phenomenon that I'm going to present. The phenomenon is called quantum gravitational spectroscopy. So we need to say a couple of things about what a spectroscopy is. Spectroscopy is the study of the interaction between matter and electromagnetic radiation. Again, most probably, you might have heard this in your chemistry class. In particular, in regards of the types of spectra that you can observe. Spectroscopy is a direct consequence of quantum mechanics. It happens because of that quantization of the orbits that I showed you a moment ago. But in particular, it is a result of the discreteness of the electromagnetic field. The atom is held together, the electrons around the nucleus is held together by the electromagnetic force, the electrostatic attraction between the positive nucleus of the atom and the negative electrons. And the fact that we are able to observe quantized orbits is a direct consequence of the fact that the electromagnetic field is not a continuous phenomenon, something that has all values from 0 to infinity, but a discrete phenomenon, that is one that only occurs at certain steps. That's what the word quantized means. Spectra can be of different types, and I'm talking about electromagnetic spectroscopy. Can be of different types. Spectra can be continuous or discrete. For example, if we analyze the spectrum of a light bulb, we take the light from the light bulb and make it go through a prism. The prism, this was observed initially by Newton, by the way. The prism will display a spectrum of all colors, right? If this is white light, it's going to show the spectrum of all the colors in the rainbow without interruptions. You're going to smoothly transition from the lowest frequency. By the way, that's what we have here. Red is the lowest frequency to the highest frequency, which is violet. Oops, I ran out of space. Okay, you get the idea. So this is high frequency. But in the case of a gas, if we take a gas that is heated up and analyze its spectrum, what we will see, or the light emitted, the radiation emitted, what we will see is that the spectrum is incomplete. Because those atoms, those electrons in the atoms of the gas are jumping up and down between discrete levels, and as a consequence, they're going to emit certain frequencies of the radiation absorbed, and not all the frequencies. On the other hand, you could have a light source that is impeded by a gas that absorbs some of the frequencies of the light source, and therefore we have a absorption spectrum. These techniques, this phenomenon is used in astronomy, so you might have heard of spectra in your astronomy class, to determine the nature, the components. For example, you hear every other day that somebody found an exoplanet that had this or that in their atmosphere. This is the method that they use. They just take the light and decompose it in a spectrum similar to the one you're seeing there, and they determine which elements uh, is the atmosphere of the planet made up of by just seeing what are the holes in the spectrum. The field of spectroscopy and modern physics have brought in several developments. For example, thanks to the observation of the spectra, the Balmer series, that was what inspired Bohr to formulate his quantization rule and his model of the hydrogen atom. The discreteness of spectra also inspired Heisenberg to develop the matrix version of quantum mechanics and Schrodinger to develop his Schrodinger equation. And later on, a phenomenon called the Lamb shift led to one of the most robust theories in physics, namely quantum electrodynamics. It looks like the list should be now uh, increased to accommodate for this other phenomenon that we refer to as quantum gravitational spectroscopy. Quantum gravitational spectroscopy is simply the observation of quantum gravitational bound states in matter. In other words, those quantization, remember that we saw those quantized orbits, that quantization phenomenon, but not in a setup where the electromagnetic force is the one that is producing it, but one where the gravitational force is producing it. QGS, especially with ultra-cold systems, is an emerging field in physics where the discreteness of the gravitational field can be observed, probed, and tested. You know, the most significant types of physics that you can do is physics that nobody has found before. That's why you hear scientists in the TV and stuff being very excited, talking about their discoveries, dark matter or whatever theory that comes to mind. It is because it's stuff that nobody has observed before, nobody has done before. And it was very exciting to hear that at the beginnings of, in the early 2000s, this phenomenon was observed. The discreteness of the gravitational field was observed because it was predicted but never attained. And this gives the opportunity to present new physics. Gravity, which is the force that you're probably most familiar with, is the least understood of all the forces in nature. These days, you keep hearing things like quantum gravity, loop quantum gravity, string theory, and stuff like that. That are suggestions on how gravity works in certain scales. In particular, this phenomenon gives us the opportunity to do just that, to study and probe gravity in certain very particular scale, microscopic scale. But in order to understand precisely what QGS is, why don't I just show you what classical gravitational spectroscopy is? And it's not hard to understand. In other words, what is the phenomenon that I'm trying to convey here? What would that phenomenon look like if we just suspended the laws of quantum mechanics and instead just considered the phenomenon in the classical world, so outside that range of sizes and energies that we mentioned at the beginning? Well, that phenomenon would look as follows. Suppose that I have a bunch of spheres or billiard balls, and we're going to throw them. Consider them to have the same mass, but we're going to throw them in the floor at different speeds. So we toss them. At the end, this is like a chamber that has a ceiling. So this is the floor, and we have a ceiling. We're going to randomly toss this bunch of spheres or billiard balls into this chamber. At the end of the chamber, there is a piece of glass. Let's say it's very thin, very fragile. We toss the balls, and the balls will bounce at different heights, right? And they will move with different speeds, and they will hit the glass. But because the glass is very, very delicate, it's very thin, let's say that they leave a mark on the glass. Well, what do you expect the results to the experiment to be if we just keep tossing more and more of these billiard balls? Well, it's not hard to see that as more and more of them are tossed, and when they hit the glass, they're going to produce a mark that we have no reason to think are not going to be marks that occur at every possible height, right? Because we're tossing those balls randomly. So they're going to hit the glass at whatever number of heights between 0 and the height of the ceiling, right? So you're going to find, let's say that this ceiling is, I don't know, 50, half a meter high. I cannot see my right hand margin. So half a meter high, 50 centimeters. So you're going to find every possible mark on the glass from 0 to 50 centimeters, provided that you repeat the experiment many, 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 many times and for a long, long time. So what we see is the gravitational version of a continuous spectrum. You don't see interruptions. You see all possible values, in this case, all possible bouncing values, right? Because when the ball reaches the glass, it's been bouncing. Here we're disregarding friction, and we're assuming that the balls don't lose any momentum when they hit the floor. All right, so this would be the appearance of the experiment in the classical world where Newton's laws and that stuff are valid. What would be the appearance of this experiment in the quantum world where Schrodinger's theory and Heisenberg's theory are valid? Well, what we would see is that these quantum particles will behave exactly like the billiard balls from the previous experiment. But as soon as we start repeating this experiment over and over, we're going to see that there are gaps. For some reason, we're going to see that some of the particles will always hit the glass at the same height, but nothing in between, or this height, but nothing in between, or this height, but nothing in between. This is what we refer to as the quantized heights. So the heights at which we observe the particles bouncing up and down are just multiples, or not multiples, but are just certain values. Not all the values are allowed, exactly in the same way in which we saw in the atom earlier, that those electrons cannot be at any possible orbit around the nucleus. They have to be at certain orbits. In other words, the spectrum of heights, if you want, is a discrete spectrum. There are gaps in between them. They don't happen at every possible height. And this is as easy as this phenomenon is. And actually, this slide is describing very well what is the appearance of the actual experiment. However, there are a lot of experimental hurdles that had to be overcome in order to the observation of this very phenomenon that you're seeing there. The reason is as follows. Let's say that we want to put together not an atom that is held together by electromagnetic forces, like the atoms that we know, but an atom that is held together by the gravitational forces. And because neutrons are going to play a big role in today's discussion, let's assume that those two particles that are going to represent our gravitational atom are neutrons, as you can see on the lower left. That atom will have certain radius. So let's see if we can find an expression for that radius by applying the rules of classical and quantum mechanics. First, we would have to equate the gravitational attraction between those neutrons with the centripetal force that they experience, right? Because if one of them is going to be orbiting around the other, then that means that there's a centripetal force, and that centripetal force has to be the gravitational force, this vector. If you equate those two quantities, then we obtain this equation. This is as far as classical mechanics can take us. In order for us to find R, we cannot go any further. Okay? But since we know that this neutron is a quantum particle and therefore it has a wave-like behavior, we can bring in some of those mathematical tools that we presented earlier. For example, the de Broglie wavelength. We know that the length, whatever the wavelength of that neutron is, it has to be wrapped around the length of the circumference. In addition, we have Heisenberg principle, uncertainty principle. No, not Heisenberg, the de Broglie wavelength. And from here, we can also plug the value of lambda there and obtain a second equation that would have this appearance. All we have to do is to combine these two because R appears in both of them. And if we do that, we obtain this expression. Indeed, this expression is indicating what are the possible orbits at which the neutron will be found in relation, the orbiting neutron will be found in relation to the one that is at its center. What will be the smallest of those radii? Because this radii increases, right? N is a number that increases from 1 in multiples, in integer numbers from 1 to infinity. What will be the smallest value of R? We call that the Bohr radius. Well, you just substitute, right? N will be equal to 1 and then determine the parentheses will be the radius. And here we would have to replace, substitute those constants. We're not going to do it accurately. It will suffice to just put more or less their values in powers of 10. So Planck's constant in powers of 10 squared divided by the gravitational constant times the mass of the neutron cubed. And you can see that something not very good is going to come out of it. The result is going to be 10 to the 21 meters, just to give you an idea. That is 100,000 light years. So they hope to see quantum bound states where we can see the discreteness of the gravitational force is pretty much impossible unless you take some actions to overcome those hurdles, as for example, the size of this ginormous gravitational atom. By the way, the reason why the number is coming out so high, and indeed the reason why this experiment had to wait until the 21st century to be observed and accomplished, is because the weakness of the gravitational force. Well, we overcome some of those difficulties, and the experimental group did this in the following way. Gravity is too weak. We have that ginormous value of the Bohr radius. Well, then don't use the gravitational force of a neutron. Use Earth's gravitational field so that that quantization is observed in Earth's gravitational field, the one that you know as 9.8 meters per second squared. Another hurdle that you will find is, well, if the particle is a quantum particle, is a very small particle, it's going to be very much influenced by electromagnetic forces from outside. And the interaction, the electromagnetic interaction is much higher than the gravitational interaction is going to throw your results off like by 1,000,000,000% error. How do we overcome that? Well, we choose a particle that is neutral, that does not have charge, and therefore it does not interact electromagnetically with anything. And that's the reason why the best particle for this experiment is a neutron, and in particular, an ultra-cold neutron. An ultra-cold neutron is simply a very slow neutron. The velocities of an ultra-cold neutron are in the order of 5 to 6 meters per second. That's pretty slow. This corresponds to a kinetic energy of the order of 100 nano electron volts. If you are in my Physics 120 class, you know what an electron volt is. In addition to that, they bounce off of surfaces very well. They have a very high reflectivity. 99% of them will bounce off. They can be kept stored at relatively low temperatures, very easily attained, 1 millikelvin. And they stay there for a long time. You know, the neutron is not stable. It will decay into other particles, but it will do it in about 15 minutes. So that's a good amount of time for you to do your experiment. So the neutron is, the ultra cold neutron in particular, is the best candidate to do this, to do this experiment. The next difficulty comes from the fact that we cannot just do the experiment that we just described a moment ago by lifting the neutron and just dropping it. The reason is that the neutron will obey the Heisenberg's uncertainty principle. No, not this Heisenberg. And therefore, there will be uncertainty in the position and momentum. The best way to overcome that is instead using not just one neutron, but a beam of neutron, a beam of ultra cold neutron. All right, that is what was attained by the experimental group in France. They call the experiment GRANITE. It stands for Gravitational Neutron-Induced Transitions. The experimental device looked like this. Yeah, I'm not going to go through too much detail. The action is really taking place and in that portion of the setup. That portion of the setup has this appearance. That neutron flow, that neutron flux, the beam of neutrons is injected in that area. The neutrons fly off. We want the neutrons that have the highest horizontal velocity so that they make it all the way to this portion of the setup. That's the one that contains two very special surfaces. We call them the mirrors. They will represent the floor and ceiling of the mock-up experiment that I showed you earlier. This is another picture of what that portion of the experimental setup looks like. That those mirrors will be located where that red circle is. And that is the part of the experiment where me and my advisor, my doctoral advisor, concentrated in. So that box, that chamber that we had earlier, that is called the waveguide. So, in physics, we always like to give fancy names to simple things. So that chamber is the waveguide. And the neutrons are injected. Okay, so the bottom surface, what we called earlier the floor, is just a very, very well-polished mirror. Okay? And the top, the ceiling, is a not very well-polished mirror. We call it the scatterer. And there is a reason for this mirror to not to be that polished. I'll explain it later. The neutron beam enters the waveguide and they bounce off in the way we saw earlier, or we explained earlier, and they will leave a pattern that describes the quantization of Earth's gravitational field, because these neutrons are bouncing up and down thanks to due to Earth's gravitational field. I have a video here. Chris, how much time do I have? We go until what time? Oh, I can't hear you.
I'd say maybe 10, 15 minutes maybe.
All right, so I'm going to skip the video. It's just an animation. If you're interested, I can send it to you guys. It's just an animation of this setup here. It just looks a little bit fancier. You get to see the neutrons and that stuff. The important bit here is that when the neutrons are detected, when they arrive, what we said earlier was a piece of glass. In reality, is a detector that has some qualities. When the detector detects the neutrons that are arriving, what they observe is that, first, before I do this, the height of this scatter can be controlled. So in the experimental setup, the scatter can be moved up and down. So they started the experiment having the scatter all the way down. What they observed was no neutron flux, so no neutrons make it because it's like the waveguide is shut down. But then they started to increase the height, no neutron flux until they reached the first quantized height. So that's like the first bar that you saw in the previous slide. They did not observe any neutrons until they hit that first height. Then, so there's a sharp increase in the neutron flux. Then there's a plateau. So no more neutrons make it until you reach the next quantized height. We call it Z2, and so on. This is the experimental data that they obtained that describes precisely that behavior. Um, there is no neutron flux until the waveguide is open at about, what is this number, 12 or 13 micrometers. Then there's a sharp increase in the neutron flux, then a plateau, then an increase, then a plateau, then an increase again, then a plateau, and so on. So this was the experimental evidence that indeed the heights were quantized. Okay. All right. This is the appearance of the laboratory where they perform this experiment. They do all sorts of experiments with neutrons over there. There's a reactor and that stuff. So what I did in my thesis? By the way, if you're interested, you can download it from this internet address. If you're interested, I can forward it to you and you can read it and then you can explain it to me because I don't know what happened there. Anyway, what I studied in my thesis was what was the role of the roughness in that scatter mirror. What we discovered was that the quality, the fineness of the spectrum that the experimenters were observing in France depended on the shape of the roughness in this scattering. We were able to develop an expression for the neutron count. So we simulated the waveguide and all that stuff. And we came to the conclusion that the number of neutrons that made it out of the waveguide could be expressed in this very particular way, where the type of roughness that the top mirror had could be expressed in this constant over here. Here's where I'm going to skip a lot of details. This quantity phi was defined in terms of a complicated integral that I don't want to go into the details of. But in any way, it was a quantity that depended on the dimensionality of the roughness. That is, if we considered the roughness to exist, I don't know, along the direction the neutrons were propagating or in a plane, let me just say it like that. Or if we consider the roughness to be distributed in a plane or in a line, it depended on some parameters of the waveguide, like the velocity of the neutrons and that stuff. But more importantly, it depended on the roughness of the waveguide, which was contained in this particular quantity. The actual dependence corresponded to the dependence of statistical quantity that it's called the correlation function. The correlation function is simply a mathematical tool that tells you, the appearance of the roughness. If you look at a rough surface, right, you know that the rough surface could be something jittery, right? Like, I don't know, if you look at the pavement when you go out, you're going to see that the pavement is rough, but the roughness will look very, very jittery. This is uncorrelated roughness. The roughness that we assumed in the rough mirror was a sort of a smooth roughness, the type that you see over here. And that type of roughness is described by that quantity that we refer to as the correlation function. So we assumed, in my thesis, we assumed that that correlation function had certain, could be described in certain mathematical ways. And in this manner, we were able to predict, we were able to fit the experimental values with a particular value of our constant. This is what we observe here. So these x's represent the experimental data points that they obtained at the laboratory in one of their runs. And we were able to kind of fit the result with a value of our constant that was roughly 23.5. These results are published in this paper if you're interested. Um, Now I'm just going to show you some images of some of the simulations that we did. They're not very impressive, so don't get too excited. But um, for example, what we did was we generated our own rough version of the rough mirror. One of those look like this. That correlation function, um, we were able to um, calculate it out of that rough surface. So one of those plots looks like this. I don't expect you to grab the ins and outs of these graphs in detail, and just to get the general idea. And at the time at which I was writing my thesis, the lab group and the experimenters were planning to run another experiment and redo some measurements. And we made some prediction as to, given their parameters, they shared their parameters with us. So we put it in our equations and in our simulations, and we estimated or predicted that the neutron count would have disappearance. So when they run the experiment, we would predict that their results would look like this. Um, all right, that's as far as I want to go in terms of what I did in my thesis. And of course, if you want more details, I'll be happy to share them with you. But probably you'll be more interested about what I'm going to say in the next 3 or so slides. And these are possible distinction projects that could involve LSMSA students. The math of the gravitational states, the quantized gravitational states, is not too hard. Essentially, it involves solving the Schrodinger equation when we put in the potential energy due to in Earth's surface, which is simply mg times the height. This has been a problem that has been solved in the past. It's called the quantum bouncer problem. But it would be interesting to have a student work out something like the wave functions, calculate the square of that, and then um, make predictions like the energy of the neutron, the position of the neutrons, and so on, the values of those heights that we observed in the experiment. The wave functions are the mathematical uh, form of those functions match what it's called the Airy functions. You can think of them as distant cousins of sine and cosine, just to give you an idea of what they mean. So that would be a very interesting project. Knowing that these wave functions would allow us to perform calculations of the quantized heights of the neutrons, their energies, their momenta, expectation values. And more importantly, since we would know exactly the wave function, we would be able to compare the calculations with the approximations, like the semi-classical approximation and all other, and some of the others that we presented earlier. Another project could be the search of a fifth force problem. You know, as I said earlier, gravity is one of the least understood forces in nature. And some physicists have proposed that there are deviations of Newton's gravitational law at the micro level, which is exactly at the level at which this experiment takes place. So solving this problem would correspond to solve Schrodinger's equation with this potential. We would have the freedom of controlling these two parameters. And this is a little bit, I will be less knowledgeable in this one. It will be interesting for me to explore what would be the results. So I would not have a clarity on what would be the exact result if we were to do this project, which is exciting because that's what projects are for. You get to learn something. All right. And another very exciting project would be the so-called neutron whispering gallery. So a variation of the experiment that I just showed you is one where the experimenters shoot the neutron into this round cavity. And what happens is that the neutron bounces off at certain heights. Again, they are quantized. So you will see them bouncing off at this height or at this height, but nothing in between. the spectrum will look like this. These bands represent those uh, portions where the detector gets hit. And it would be interesting to involve a student that calculates this wave functions, for example. So what would be the appearance of the wave function? In this case, it would be interesting because by the that um, waveguide being now curved, the symmetries are different. So interesting math and physics for sure will be guaranteed. Another question that we could ask with this project is, well, what if we include roughness? So we did roughness in the straight waveguide. What would be the effect of roughness in this waveguide? So that would be interesting. And just to add, I have other research interests that may match something that you like. In my master's thesis, I worked in superconductivity and Bose-Einstein condensation, which is low temperature physics. It will be interesting to do a project on that if that's something that interests you. And I am learning general relativity to do black hole physics. So if black holes are something that you want to understand in more detail, then that's something that we can put together a project for. All right. As conclusions, the observations of gravitational states of matter were attained experimentally by that granite group in France, which makes use of the convenient properties of ultra-cold neutrons to produce those gravitational states. If we understand the role of the roughness, then we can improve those experimental results. So a study of roughness in the waveguide will be productive. This constant contains all the information that we would need in order to do such calculation. Um, we could generate surfaces where we know the roughness of it, and then extract the correlations and see uh, how much of an error we introduce because of not knowing how the roughness of the surfaces are. Potential applications of this phenomena, QGS, include what we just said a moment ago, tests. Well, I did not include this one actually, tests of the weak equivalent principle, tests of the gravitational square law at the micro level, um, tests of the fifth force, etc. These are not, by the way, the ones I mentioned are not just the only applications of this phenomenon. They go something as far as astronomy and astrophysics, which I did not include in this discussion. Okay, so that's all I wanted to say, and and now I wonder if you guys have any questions for me.
All right, y'all have any questions here in chat or unmuting? Don't be bashful. I actually have a couple questions. I mean, do I need to
Yeah,
break the ice, like break the ice and ask a few questions, and then y'all will get brave or something? Um,
yeah.
from things we've seen in chemistry, you had one of your spectra, you had like bright, there's like a bright line, and then right next to it
Mm-hmm.
there was a very faint line.
Let's
Um,
see.
and the difference in those brightness is just basically how many more of those particular photons were
Yep.
present versus a smaller number of the other quantized energy.
You mean this graph?
No, no, no. Way back at the beginning, you had some
Oh,
line spectra, some line emission. And I never
oh
pondered
okay.
this in chemistry. It's like, why are some of the lines brighter than others?
Mm-hmm.
And is that just simply
Yeah,
there's
it would
more
be.
probability of this particular energy level versus that one?
Yeah, it would be judged by the number of neutrons that hit. I don't know if it's
Yeah,
anything.
right there. Okay, so I see a pronounced green and then a very faint green line.
Yeah, yeah. So the intensity was something that I did not concentrate in the case of the neutrons, that is. It's something that
I never
I did
knew
not.
understood what gives rise to that. Like, I mean, is it really bright because there's more photons with that energy? And then the other
Mm,
one is another energy level that can exist, but not as many
yeah,
photons in that.
it's the number of neutrons, but well,
Well, in
that
that case, I guess it was photons is what was kind of
sorry, the number of photons. You're right.
photons come through. Yeah.
Um, but it escapes me what would be the reason why the intensity
Okay.
varies. I think it has to do with the temperature, but right,
Okay.
because for a given temperature, you don't get all photons absorbing and emitting. They obey like some sort of curve. So I
Okay.
think that might be the reason, but I'm not sure.
Okay. And then there was another picture where you had like I think it was the same slide. Once that continuous light passes through material, the bottom one there where you've got the light, it passes through the cold gas,
Yeah,
and then you see the absorption spectrum.
yeah.
Would there be like an equivalent to this gravitational thing where you have these different particles passing, I'll say passing through something
Hmm.
that would produce an absorption spectrum depending upon what that something was? I don't know how to explain it, but
Yeah, yeah, I know what you mean. The thing is that
I mean,
these
I don't know if you could call it a physical object that would pass through, but a field that would show an absorption spectrum or something. But
it would be something that if we have a let me think, that's a good question. Um, it would be something that would be absorbing the neutrons in some
uh-huh,
way
yeah, yeah,
at
it'd be absorbing
certain
the neutrons
at
somehow.
certain heights. I know that there's a variation. Maybe this answers your question. There's a variation of the experiment that I studied where they take the mirror and they make it vibrate. Okay, so by making the mirror vibrate, they cause some neutrons to that were jumping, let's say, this high, to now just jump, let's say, this high, or jump from one of the heights to the other. So in that way, that could be like the neutron absorbs some photon, so to speak, and then stays only bouncing between those two heights and not the original one. I think that is more or less the gravitational equivalent to that
Yeah, my
that
temptation is to
idea that
take
you're.
all the things I know about photons and say, man, is there like an equivalent to the gravitational uh observations we're seeing? And then the last question I had is you had this roughness factor. Now that's like just a random rough surface, right?
No, that's the thing. It's not random roughness. That's why we
Or
call
it
it
falls
core.
within a tight window of high peaks and valleys in the surface or
Yeah.
something.
So when you how to say it? Let's say when you turn on the TV in a dead channel, you see truly
Mm-hmm.
random static,
Yeah, yeah.
right? If something pops up here, that does not influence something popping up over here. But the roughness, the randomness that we assumed for our surface was correlated roughness, which means that something popping up over here or a certain height in the profile over here influences whether or not we have a similar height over here. And in this way, the profile was not so rough. It
Uh-huh.
was
Yeah,
sort of
yeah.
smooth, and that's the simplest type of roughness that that would simplify the calculations, and that's why we adopted it.
Yeah, I mean, because
Yeah.
roughness, I mean, the first thing that came into my mind is what if your top rough surface was actually had predictable grooves in it or something? I mean, something that wasn't kind of random but had a predictability, and
Yeah, and
did
that
that
was
in any way
the idea.
change?
The idea for us was to convince the experimenters that they should have some sort of control over the roughness of that top mirror, and we were proposing the different types of roughness that they could generate so that the observation um, of the quantized levels was the most accurate. And one thing I forgot to mention, the roughness of the top ceiling is important because that top ceiling, for a reason that I did not have time to go into, absorbs some of the neutrons. The fastest neutrons are not reflected off. The reason why the surface is rough is so that it absorbs the fast neutrons because only the ones that are have the highest horizontal speed but the lowest vertical speed.
Hmm.
So that rough scatter would absorb the undesired neutrons,
Yeah.
and we saw that that plays a role, that the roughness plays a role in the optimization of that absorption.
Yeah.
So
Okay. Any students? Any of y'all have any questions out there? Anything? Nothing?
if any of you guys feel that any of the projects I mentioned appeal to you in any way, not necessarily the ones related with neutrons, but maybe the other two, low temperature physics or black holes or any of that, my office is 313 in HSB. So just pay me a visit or just send me an email, and then we can um, talk about it.
Okay. All right. Well, y'all are certainly being bashful today. Okay. Oh, all right.
All right, you're welcome.
Okay. All right. Well, I guess if nobody has any questions, we'll turn all of y'all loose. Thank you. Thank you very much again, Dr. Escobar, for
Yeah, sure.
taking your time to do this presentation and stop by his office sometime.
All
All
right.
right. Y'all take care.
Yep. Bye bye.